This video is part of my project on creating model railway traffic lights. In this video I'm going to be using KiCad to create a printed circuit board to control the lights. In my previous videos I've shown how I designed the traffic lights in FreeCAD and then 3D printed that. I've also shown how it can be controlled using the Raspberry Pi Pico microcontroller. In this video I'm going to take it one step further in showing how this could be made into a custom printed circuit board, or PCB, based around the ATmega 328B microcontroller. This is the same microcontroller used in the Arduino UNO and similar boards. I've got our KiCad running here, and I'm going to just start by first creating a new project. Ensure the create a new directory is ticked and then just give it a name. I'm going to call this one custom Arduino. Basic, I'm going to implement the basic features of the Arduino and 3 LEDs for our traffic light. This is a simpler version. I've already created one called traffic light, but that just took far too long to create to be able to be a useful demonstration. So created this, it's called custom Arduino project, and what KiCad is a collection of tools rather than being one application that does everything. There's Eeschema, which is the schematic layout editor, which we'll be using to create the schematic diagram. A symbol editor if you want to create custom symbols. We don't expect to be using that. PCB layout editor, PCB new, we'll certainly be using that to create the PCB. Custom footprint editor if we need to use that. A Gerber viewer which we can use to check the output to make sure it meets what we're expecting. There's a bitmap converter used for adding images. We probably won't do that in this video. PCB calculator with some useful calculation tools in it, and page layout which you can use if you want a custom page, but we're just going to stick to the basic. We're going to look at the main components, which is schematic layout, then we'll put that into a PCB layout, and then we'll look at the output. And each of the tools creates different files. So at the moment we've got the schematic files being created for us and one for the PCB layout. Let's launch Eeschema, the schematic layout tool, and we're going to start by just set some preferences. So there's a few icons on here. I'm going to be working in millimeters. You can turn the grid on and off and change the grid if you want, and we're going to try and have right angle corners. And if you want to change, there's more preferences elsewhere, things like the operation of your mouse, which you might want to change, because it was I made some changes so it didn't keep following me as I zoomed in and things like that, but that's up to you. But the one thing is worth looking at for when you start a project is going into the page settings, and this is going to populate this information that's in the bottom right hand corner of the diagram. I've set it to A4 landscape. I'm in the UK, hence A4, and millimeters I'm going to be using. It's using the ISO date format. This is my first version, so I'm going to call it version 1.0. Title, this is a custom Arduino circuit. So company, you might want to put your own name in here or whatever you want. I'm going to put my website address in so that people know where to find more information on it, and then you can put comments about what it is, what it does. And these are actually ordered in reverse, so this one would be at the top down to this one at the bottom. I'm just going to put a single line of custom Arduino-like circuit. And we're not going to be implementing everything in the Arduino, just the basic core features. And as you can see, this is now populated the information in the bottom right. And other than that, we've got a fairly blank screen. And this is where we're going to start by creating a schematic diagram. The tools to do this are on the right hand side, and you can click these tools, although quite often you get used to using shortcuts because it's going to be a lot quicker than having to move over to these all the time. And the first one I'm going to use is place symbol. I'll use the place symbol. The shortcut key is A, which I think is add symbol. And we're going to start with the main processor of the Arduino UNO is the 18 Mega 328P. And that's part of the standard library, so that's great. And there's a few different versions. I'll make this a little bigger so you can see all the writing. And the main thing is we're looking for one with a dual inline package, which is the DIP package, this one here. And that will automatically be associated with the appropriate footprint, which some components do, others don't. We'll come to that later. Just click to place that, and as you can see, this one is laid out with most of the pins to the right hand side. Power is top and bottom, that's quite common, and then we've got the A ref just to the side. Let's start by creating the power input to this. But I'm not going to be wiring everything. I'm going to be using power labels, which I'll show you in a minute. We'll start with the circuit over here. I'm going to start with having this, the power is going to come in on a screw terminal. So A to add, or I could have clicked up on here, and I want a screw terminal. So you see there's lots come up already. I want one that's 1 by 2. That's right. Let's put that there. Now I'm going to flip this one. So I just right click and mirror around the horizontal axis. And mirror the vertical. So that the pins are in the right place. I'm going to put some power connectors on here. Let's start with a ground. And for the power connectors, it's like adding a component. Just click on that and there'll be a ground you can use. Let's place this over here and go to add another one, which will be plus 5 volts. And this is the initial 5 volts as it comes into the circuit. And then we can wire these components up by putting it at the start point, pressing the W key, or you can use this green place wire option here. Now what this will allow us to do is, if we created more of these labels and put them around, I'll take this ground one and I'm going to copy this one. I'm going to use the C key for copy, and if we put that here and then we can wire that up as well. This ground is also connected to this ground and any other ground symbol using the same label. The same with the +5 volts. If we put that elsewhere, then that would also be connected to the same point. I'm going to though put a diode in here to protect against reverse connecting the power the wrong way around and potentially causing some damage. So let's put a diode in. I use the A key, and I know the particular diode I'm going to use, which is a 1N4007. That's quite a common one, and so it's part of the library. It's facing the wrong way though. I want it to go from left to right, so if I press the R key to rotate, I can rotate that so it's facing the right direction. And then I can wire that to there. And then I can add a new reference here so that I'm using this, the power from this end rather than the other end. So I'm going to add another power connector. It's still going to be +5 volts. It's going to have dropped a little bit because of the diode. I'll just call it 5 volt A, and it's just a reference that we can use. Put that up there, and then use the wire to that. And now we've got that +5 volts A. We can copy that and use that for the VCC and the analog VCC for the 80 mega. Now I'm also going to put some capacitors on here. It's a bit smoother capacitors. So start off with a 10 microfarad capacitor, and this would be an electrolytic capacitor, so it's polarized. So A to add. I'm still in the wiring mode, just escape out that. Escape again. Oops. Add. Then start typing capacitor. I'm in the wrong place, so start adding capacitor up here. And here we go. So this one cap is for simulation only. These are in PSpice, so we don't want those. We want the actual capacitors. And down here we've got C, which is unpolarized, but this one's going to be polarized because it's electrolytic, so we'll go for CP. Put that here. I'm going to put that before the diode. Doesn't really matter, but press W to go back into the wire mode. You'll see that the green arrow, the green line is highlighted, and it's put us into that mode. You can wire that up there, and then really I don't like the way these lines are. I'm just going to move these around a bit. So let's just press M over the ground and move that. You notice it doesn't move the line though, it just moves the components that you've selected. And if I delete this by hovering over it and press the delete key, I can now wire these up a bit nicer. There we go. And I'm going to add 2 more capacitors as well. And these are going to be bypass capacitors, which will be placed close to the chip. But even though physically they're going to be close to the chip, I'm still going to put them in this power section over here, so it just keeps everything tidy. So I'll add capacitor, and this time we can use the unpolarized version, and we'll put that there, and I'm going to add another. I'll just wire this one up first, I'll explain. Press wire, W to get to the Y mode. We can wire that one up, wire up to there. Now once we've added these, we can change these values. It's got, you can see all the components have got a question mark next to them, and that's the annotation. That's just a numbering for each set of components. We won't worry about those until quite close to the end. But then the second value is the value. As you can see on the diode, it's got the part number. On the capacitor, we want to put the value of the capacitor in there. If you put the cursor over the component and press E for edit, it edits the properties, and we can change this value, and for this one it's going to be 10 microfarads, and for this one we'll put it over there, press E, I'm going to make this 100 nanofarads, so these are much smaller. And now I've set this as 100 nanofarads one, I can just copy that one. And you see the copy is also 100 nanofarads. Let's just wire that up. And that's the power part of the circuitry essentially done. It doesn't have the proper voltage regulators and things like that that the proper Arduino does. Instead, this is relying on us having a nice stable 5-volt power supply. Actually, it could vary. It could be as low as 3.3 volts. It needs to be a bit higher because of the diode. But 5 volts is quite a nice voltage. It's a typical supply to have. One more thing, I'd like to add a little indicator to indicate that it's powered on. But I don't want to use a big LED. What I want to do is actually use a little surface mount component. Now this is going to make it more tricky to solder up. So this will be an optional component. I'm just going to pop this on here anyway, and it can be created on the PCB, and then if you're not up to soldering SMD component, then don't bother. But if you do, then it's a nice little feature to add. I'm going to just press add, as A for add, and for the diode there's going to have to be a resistor. For most purposes I'll just use this standard R one, but because I'm going to put an SMD one, I want to make it clear on the diagram that this is a small resistor, so I'm going to use the R small footprint. Put that there, and same for the LED. There's an LED small as well. So I'll use that. Rotate that so it lines up, and then we can just wire those in. And that gives us a little bit of an opportunity later to see how SMD components will be created on the printed circuit board, and how you can solder those and what they look like, etc. We've now got the 18 mega and we've got the power supply. The next bit is to add the crystal and the crystal circuitry, which is going to go on here. These are the pins for the crystal. Now I could try and put all the components here, or just like we use the ground to indicate that these are connected, we can use other labels to indicate that these components are going to be elsewhere on this diagram, because otherwise it would be very, very cluttered in this area. I'm going to pretty much be using these labels for a lot of things when you're doing circuits. So the labels, I'm going to call them Crystal 1, rotate, and another one which will be called Crystal 2. Now you notice there are asking for different shapes. This can be used to indicate whether this is an input and output. I'm not getting into that level of detail at this stage. I'm just going to put a standard one and then we'll sort the rest out later. So just wire those up. Then we can add our crystal. Just A to add a component, crystal, and we just want a standard 2-pin crystal, and we can put that here, and we can take these and copy these to either side, and that's W, and we're going to wire mode. Now for additional stability for the clock circuit, we can add a couple of capacitors on these as well that connect to ground. We could just copy one from here, we could add another one. I'm going to copy one from here, but we don't want 100 nanofarads. We want these to be a lot smaller. These are going to be 22 picofarads. So if we just click E to edit, and we'll just change that. That's now a 22 picofarad. Now we can copy that, and we'll have another one there. And these go to ground, so if we just take a copy of the ground, and then we can wire these up. And that is pretty much the most basic Arduino-like 80 megabase circuit you can create. So we've got a power supply and we've got the crystal circuitry, and that would run. But we're not going to be able to program it like that, so we need a little bit of circuitry so that we can connect a UART to it. Now on the normal Arduino board, the UART will be mounted on the Arduino. We're going to use an external UART that can be plugged in as required. Program it, then you can remove the UART. You don't need to use those components. So like we did with this, I use a screw terminal here. I'm going to use a pin header so that we can plug the wires that go to the UART, so using DuPont type connectors like that. So connectors are part of the component listers, or component list or symbol list, and we can just type connector, and we're going to need 5 pins on this. So we could scroll down, it's actually down there, but we could scroll down, or we can type 01 times 05. 1 row, 5 pins, 1 to 5. And there's a generic one, or there's this male one. Just take the male connector. We'll just put that up here, so we can build our UART circuitry around here. So I'm going to use the same order as another circuit I've made previously. So the top one is going to go to the data ready. In fact, I'll write this in text next to here. So I've just clicked on the text button. I can put on here. The top one will be data ready. Then the next pin will be the transmit from the UART, which actually goes to the receive of the 18 mega 328. Then the receive of the UART, which goes to the transmit of the 18 mega. The 5 volts power supply if we want to power it from the UART, and a ground connection. And see, that almost lines up. Just if you go back into the properties, you've got the text size. You can just put 1.3. It just spreads it out a little bit more. So the data ready is used for the reset. So this will trigger a reset, loads the bootloader and allows us to load our code. And it first goes through a capacitor. I'll just add a new capacitor here. Could copy one of the existing ones. I'm going to just rotate that and edit that, so that wants to have a value of 100 nanofarads. And it has a pull-up resistor to the positive supply. So and there, and then it's got to go to the reset pin, which is this one here, reset. So we'll use a label for that. Copy that and use the C key, copy that, and then we can wire all these up. And that's the reset data ready part. The receive and transmit want to go from these pins down to pins 2 and 3, and we don't want to drag the wires all across the board, so again we'll just use global labels. Top one is the receive. And transmit. And we can copy these. And then wire them up. Now, if it looks odd that transmit goes to receive and receive goes to transmit, then that's how serial UART connections work. That the transmit of one goes to the receive of the other. Then we've got the 5 volt supply. Start off by just taking the ground, just copy one of the existing ones, and that's going to go there. And the 5 volt supply, I could just wire it straight into the 5 volt, but I'm going to put this through another diode. You shouldn't shouldn't ever have it powered by two sources, so you should never connect this UART at the same time as there's a power supply down here. But just in case they do, then I want to put a bit of extra protection in. I'll just stick a diode in there, and just again the 1N4007, just because I've got a drawer full of them rather than any other reason. And this will go to the plus 5 volt supply, so I can copy that and then wire this all up. Then the final part of the circuit is going to be our LEDs. So we're going to have 3 LEDs, a red, green and amber, which will be connected to some of the digital outputs. Now I'm just going to use outputs 2, 3 and 4. As before, I'm going to use labels rather than having wires running everywhere. So and again I can copy these as long as I change that value using edit properties, using the E key. And then I can copy these labels. Actually, I can copy all 3 together by selecting them, pressing C, in fact no, sorry, right clicking and copying the block and then pasting it. And I want to select it again and then mirror around vertical axes and have them in order. I'll just move these around using the M key just to space them. A little better. And I'll just wire these up so I don't get forgotten. And then over here I just need 3 resistors and then 3 LEDs. Just pressing the C to copy, easy enough to add, and then an LED. Now you could denote the colour and everything using different LEDs. I'll just use a standard LED for now. And then these all need to go to a ground. Just put a single ground, real connector. Just wire these up. Now one thing you'll notice is that all the text or the writing is offset, so we just need to move that. Just like when you press M to move over a component, it'll move the component and all its labels. If you just press M over the label, make sure I'm in the arrow mode, then it'll just move that one particular thing. And if there's could be different things that you're choosing, then it'll give you the option which one do you want to select. So it's the question. Oh, sorry. It's the field reference is the one we wanted to move. So I'm actually putting the reference inside the component. And then do the same for the LEDs. And we can edit these to say which colour they are. So if we replace that with, instead of LED, it says red. Now you might think we'd use all the same value resistors because we've got 3 LEDs and they're all going to be the same physical size. In this case 8mm LEDs, they're quite large ones. However, the different colours have different voltage drops across them and different intensities at different amounts of current. So based on that, did some calculations and basically substituted some resistors in to try, and decided that to get sensible amount of brightness from each one, I used 220 ohms for the red and amber ones and then a 330 ohm for the green. So I just use the edit properties to change these. Another 220 ohms and then this one 330 ohms. So that's pretty much the circuit done. One more thing, I'll just put a capacitor on the AREF as well. 100 nanofarads, I could just copy one of our existing ones. And that just goes to ground. Now I can just have a quick look around the diagram, make sure it's everything I wanted. That looks like it. So the circles denote wires crossing. If you've got two wires that are connected directly, you don't normally get a circle, and if you've got two wires that cross at right angles that don't connect, then you don't get a dot. So I'm guessing that looks like I've overstretched a little bit, so I'll just delete that. Horizontal wire, oh there we go, that looks better. And I missed actually the voltage on the pull-up resistor. Just rename this connector here to be the UART connection. Same with this one, instead of saying screw terminal, I'll say power. All looks good. Now, found another instance. Looks like I've overshot. With that one as well. Now there's a rules checker, electrical rules checker on here, but there's a few things I need to do before I run that. The first thing is that any ports that are not used will flag up an error because they're not connected to anything. Oh, just delete that line as well. That's going to cause a problem, that short circuit. So as I go through, I'll just mark all these as not used, intentionally not used, by putting a little cross next to them. And that way the rules checker knows, don't bother checking to see if there's something connected. Actually, it'll give an error if something is connected. Now there's one more thing that's going to fail the rules checker, but I'll actually let it fail so that you can see how to use the rules checker and how we can fix that. So we'll go to electrical rules checker and just click run. Yeah, before we do that, we just need to annotate them, so we can use this button which will automatically annotate them. So annotation is to add numbers instead of these question marks, so that they're sequentially numbered, the diodes for instance, things like that. And we can let it do them automatically. However, sometimes it's nice to be able to specify some particular ones. In particular here, it'd be nice if this diode and this resistor number match. Not required, but it'll make it a little bit easier for when we're soldering, for instance. So I'm just going to edit these ones, which you can do through the edit, and we'll call this one R1 and this one D1. Now we'll do the same for this, that one too. That one 3. Then I can automatically do the annotation of the rest. So now they've all got unique numbers now. Now we can do the rules checker. Click run. And as I expected, there's a couple of errors, 3 errors, and this is about pins not being driven by any pin, which is a bit of a cryptic message. But what this is, and it's quite a common thing, is that if you create a circuit, then it's expecting there to be a power supply on that circuit. But our power supply is coming from this connector, so it doesn't know that this is a power supply. So we just need to add a reference. And as you can see, there's little green arrows telling you where the errors are. So we need one on the plus 5 volt, on the plus 5A, and one on the ground, which I think is indicated on this one. There's just one arrow per circuit, and that's to help you find your errors. So there's a way around this on KiCad, and that's to use a special power connector called a power reference. So we're going to the power, add, if that's not a reference, power flag. That's what I was looking for. So if we put power flag on there, put one here as well. And one here. We just wire those up. And unlike the other labels, where if they've got the same name they're physically connected, the power flag is a special one and it doesn't actually connect any of these together, because otherwise it would cause a short circuit. So now we should be able to run the tools checker again, and we've got no errors, so we successfully created a circuit. So at this point I'll just save it. Now could spend a little bit more time tidying up, moving some of these labels around, but I'm going to leave it there for this video. The schematic diagram is now complete and it's ready to start converting that into a printed circuit board design. That will be on the next video. I'll include a link in the next video once it's uploaded. I hope you found that useful. Thanks for watching, and I look forward to seeing you in the next part of the video.